Okay, we have our ship. It turns, but then if I turn it, let's say I'll turn to the left a little bit, I'll push up, and it goes straight up instead of to the upper left, and that is not what we desire. So in this video, let's talk about how to fix that. First, I'm going to draw, you know what, I'm going to draw this ultra thin. I've never tried super thin. Oh man, that's going to accentuate my inability to draw straight. Ooh. That's kind of straight. Okay, and then that one's not so straight. Remember we have the three vertices that make up the ship. We have the one that points straight up like this to make the tip, and then we have the other two that come down here. If I can figure out where the tip's going, then I know the direction of the ship. I'm going to ignore the bottom left and bottom right vertices for now. Let's say I turn my ship to point to the upper left like I just did. So that means I'm going to sweep out an angle here, theta. That's theta. And my resulting vector, I'm simply rotating that vector by that amount. Well, what is that amount? Well, let's just go back to some, hopefully this looks familiar, but I'm going to break this rotated vector out into its individual components. Okay, so there's the y component, there's the x component. So what direction is that? Well, what is the length of this side? We've seen this before. I'm going to get rid of theta for now. What's the length of this top side? Again, it's SOHCAHTOA. And then there's TOA, but we're not really worried about TOA for now. It's opposite over hypotenuse. For the length of this, the theta, remember, is this angle, and the opposite of this angle is this side. Well, that's opposite over hypotenuse. Well, remember, the hypotenuse is still 1. All right, as far as the rotation goes, when we're rotating a vector, it's 1, and the length of our ship, it's not 1, but I really don't care. I'm just worried about the direction. Again, we're thinking here in unit vectors. I'm not necessarily worried about the magnitude. What's the rotation here? So the hypotenuse will be 1, and so basically the sine of theta is opposite over hypotenuse, but if you remember, hypotenuse is 1, so we can just say it's equal to the opposite. Okay, that's an O. And then what's the length? Oh, but it's negative sine. Okay, we're going negative direction, negative x. And then what's the length of this side? Well, this is the cosine. It's the adjacent of this angle. All right, and that's the adjacent over the hypotenuse. So the adjacent. So cosine theta is equal to adjacent over hypotenuse. But again, unit vectors, normalized vectors, the hypotenuse is 1, so I'm not interested in that. So cosine, or the length of that side, the y, is cosine theta. So all I need to do to get a unit length vector with this direction is make a vector 2 with the y, or the x, being negative sine theta, and the y being cosine theta. Alright, I hope this is review, because we did a lot of this when we were doing the rotate function on the matrix earlier. But let's use that. I'm gonna shut this down. Let's use that and see if we can get the direction. When we accelerate here, where is it? Right here. Update velocity. Well, actually, that should be update acceleration, should it not? Okay, we do the velocity update. Oh, no, we do the velocity update right here. Yes, we are updating velocity. Sorry, a little brain skip there. Let's say vector 2D direction to accelerate. I know that's a long name, but let's just put that there. And then all I need to do is negative sine. Let's bring this. Can I take this off the screen? Does that? There we go. Negative sine. Negative sine of what? Well, it's that angle we're storing. Where is that angle? Ship orientation. So ship orientation. And then it's going to be cosine ship orientation. And then instead of saying ship velocity dot y plus equals acceleration, we're just going to say the ship velocity is the acceleration. Okay, notice we get the red squiggly immediately. It's saying I can't add a scalar to a vector. That's not defined. All right, again, you want to accelerate 0 to 60 in 8 seconds. That's fine. but I need to know the direction as well. Well, we have the direction here, and it's unit length, so all I have to do to get a direction is say, well, direction to accelerate times the acceleration. And here I've combined a direction, I've combined a magnitude. I'm using that, I'm combining them via the multiplication operator, which we defined for vector 2. And that returns a vector. And now we have the ship velocity. We can add that to the ship velocity. Okay, so Control F5, build this, run this. Let's turn, and I'm going to push forward now. You see, we accelerate the proper way. And now I'm going to point down. Oh, we went off the screen. Let's restart. I've lost my ship. We're going to handle boundaries, not too far out. But here we go, going up. And then let's turn right, and then going right. And then let's go down, and going down, and so on and so forth. So there you go. That's the simple way, probably the most straightforward way to get the direction is we just say, well, it's a sine, or it's a negative sign, and it's a cosine. Call it good. But hopefully this looks familiar, this negative sign, cosine. Where have we seen that before? And if you remember, we go over here to our math library. We got this INL file. We got this rotate. And I vaguely remember having to use a negative sign and a cosine. And if you recall from the matrix videos, these are basis vectors. And all of a sudden, it's the same logic. It's the exact same thing we did here to rotate that one vector, but we're only trying to create that one vector out of that direction, and so we use this side. But I could, if I wanted to, and I definitely could do this. Let me show you a different way of pulling the direction out by reusing our logic here. What I'm going to do instead is say, you know what? I know my ship's tip is pointing straight up. That's where I've defined this as the developer of this game, so to say, that the tip of the ship is straight up in the y direction. I don't care how far it is. It could be way up here or way down here. It doesn't matter. I'm just interested in the direction again. Alright, so I can say, let's go back over here to update velocity. And I could, instead of doing this, which I think is quite nice and straightforward, I could instead say, well, vector 2D straight up for my ship, that is 0 in the x, but 1 in the y. And now I've made a unit length vector. Its length is 1, its direction straight up. And all I need to do now is essentially do what we did up here when we rendered our triangle, when we applied this matrix. We just say, hey, get this rotation matrix and multiply it against the individual, or multiply it against the vertex I just created. So yes, we made this matrix and we applied it to each of the vertices one by one so we could draw, but down here I can use that for acceleration as well. So I'm going to say matrix 2D, and maybe not as efficient, but I'm going to call it op. Same thing we had up above, matrix 2D, rotate, ship orientation. And now I'll take what's defined as up for my ship. I'll hit it with this rotation matrix, and out will pop the direction to accelerate. So I'm going to comment this out now just to prove that this really works. Vector 2D direction to accelerate. Again, it's the direction, not necessarily the magnitude. Gets our operator applied to what it means to be straight up for my ship. And then you'll see that, well, let's Control F5 this, and the result's the same. Let's turn to the right this time, and we accelerate right. Now let's go down, and let's go left, and so on and so forth. So we're getting this asteroids feel to our game. That's kind of nice, right? Well, think about it. Let's think about what's really going on here. In fact, I'm actually going to work this one out by hand. Okay, our operator that we defined, this matrix here, when we say rotate ship orientation, remember that just gives us cosine, sine, that's the first basis vector, and then we got negative sine and cosine here for the second basis vector. Let me wrap this up around our basis vectors to remember that these are basis vectors, and the matrix isn't a big scary thing that we need to be scared of. Okay, well, what does it mean to be straight up for our ship? Well, that essentially means straight up for our ship. Remember, we define this vector as 0, 1. So we're multiplying this matrix against this vector. Well, what's that going to give us? It's essentially the same as saying 0 times this basis vector plus 1 times this basis vector. Well, 0 times this means it just goes away. So then we're left with 1 times negative sine cosine. Okay, negative sine and cosine. Now wait a minute. Wait a minute. Wait a minute. Isn't that what we used right here? Negative sine and cosine? Huh? No, it's not as magical as it probably appears. There it is. I don't Now let's think about what I'm doing here. When we take a vector like this, and I say let's make all the components 0. In this case, we only have one component we can make 0. But this works as well in 3D and 4D and 5D and 6D. But we're not going to get nearly that dimensional. We'll go 3D. But for now, we make all the components 0, and then we just make one of the components 1. Well, that simply is a way of extracting the basis vector out of the matrix that you're applying to it. Okay, let me see if I can illustrate this in 3D. So say we have, let me go a little thicker there, and let's go blue. So in 3D, you'll see that it works pretty much the same. It is the same, 0 or 1 0 0 0 1 0. Don't worry, we'll go 3D, not in the near future, but soon enough. So this is a 3D vector, and this is the orthonormal basis. Again, normal or ortho means perpendicular to each other, and ortho means orthonormal. Sorry, ortho perpendicular, normal. They're unit length 1. Okay, so we're used to this 2 directions. We've been doing 2D, but then I've added this third direction. Let's just say positive z is that way. Okay, now we're going 3D. But if I take a vector and let's go green, and I say, well, I want to know what the y component looks like. Well, that's simple. I just have to. What's this matrix going to do to the y component? Well, 0 1 0. That means it's going to be 0 times this basis vector plus 1, this 1, times this basis vector plus 0 times this basis vector. Well, 0 times this is going to eliminate it, and 0 times that's going to eliminate it, and so all we'll be left over with is this basis vector. So anyway, I'm going to leave this. If you notice, to create the matrix, because we have to do the cosine, negative sine, sine, cosine, we have to do all that work and build this object, and we did optimize this a little bit, but I'm actually going to, I don't know, I think I'll just stick with this approach instead, because I think it's less work and a little simpler, and it makes sense that, yeah, it's still length 1. Remember the trig identity, sine squared plus cosine squared is length 1. And then I don't have to create this other part of the matrix or this other basis vector that I'm just going to throw away. So I'm going to stick with this, and I think this was a good educational tool, but I'm going to eliminate that. Control F5, make sure this still works. And turn, accelerate, turn, accelerate, turn, accelerate. That's something I can be proud of, and that's fun. That's fun. I know all we have is a simple ship here that we can turn and accelerate, but think of all the videos it's taken to get up to this point. And I'm really, like, again, I'm just trying to go pro. I'm trying to do it how a pro engine would be, and of course it takes a long time to explain this stuff, and I'm very thorough and I'm very slow. I try to add all the details that you'll need to understand, and hopefully it works for you.